Hola.
Did Tony freeze?
There.
I believe Tony froze. So hi everybody. Welcome to this week's Hubble Hangout. After a few weeks on hiatus, we are back after the 25th anniversary, and we are going over some amazing observations that have been made, not only with the Hubble Space Telescope, but also with Spitzer and confirmed by Keck. And I think Tony's feed's coming back. I'm not sure. Are you there, Tony?
Am I there now? Am I there?
You are there.
Okay.
So I'll let you take it from here.
All right, thanks, guys. Well, we are, as Scott said, we are back from our very short hiatus, and we are getting ready. We have a very interesting hangout planned for you today. My name is Tony Darnell. I work at the Space Telescope Science Institute, and today's hangout is all about, and get ready to hear these words a lot, folks, astronomers using the Hubble Space Telescope have found a new most distant galaxy. And the reason you're going to keep hearing this in the future is that astronomers are pushing Hubble pretty hard to look at some of the earliest galaxies in the universe. And so this is all in advance of the James Webb Space Telescope. We're trying to learn as much as we can about the very early galaxies that were first formed. And in this case, the galaxy is very adorably named EGS-ZS8-1, and we are going to talk all about its properties and characteristics and things like that. But before we get going, I want to remind you guys that while the Hubble 25th anniversary is officially over, the actual date of the anniversary, there's still going to be events going on all year long. So I would invite you to visit Hubble 25th is very important, .org, and go and check out whatever events are going on in your area and around the country for Hubble 25th celebrations. So we hope you can do that. We also want you, and before I introduce my guest for today, I want to remind you that we are very much interested in hearing from you. So we hope that you will give us your comments and questions. We've got a lot of interesting things to talk about today. And Scott Lewis, the driver of the internet, can you please tell these kind people how they can interact with us?
Absolutely. So the best and easiest way for us to answer your questions and comments is to use the Q&A app here on YouTube and Google+. You can utilize it both there. So on the bottom left-hand side on YouTube, you'll see that we are answering questions, and you'll be able to input those questions there. We will see them and select them, and we'll timestamp it and let us actually place those in there when they're answering your questions. We're also live tweeting this, so we're using the hashtag Hubble Hangout. So I'm sure you see it down here on the very bottom. And also we'll be checking out Hubble 25 as well, because it is still a celebration of the 25th anniversary of the Hubble Space Telescope.
That's right. So if you haven't followed us on @HubbleTelescope on Twitter, you need to do that, and also subscribe to our YouTube channel, Hubble Site Channel, and you'll be able to catch all the announcements as they come out. So looking forward to hearing from you, and if any of your comments or questions come through as the comment or as the Hangout progresses, I'll read them out there. Otherwise, I'll wait until the end. So as I said before, a new most distant galaxy ringing in at about 15% of the mass of our sun, EGS-ZS8-1, was seen by the Hubble Space Telescope at a time when the universe was about 670 million years old, which means that the first photons left that galaxy and then traveled over 13 billion years before its feeble photons landed on the detectors of our venerable Hubble Space Telescope. But that's not the only instrument that used it. We also have observations from Spitzer and observations from the ground-based observatory on top of Mauna Kea, known as Keck. So we'll be talking about how all of these instruments work together. And the scientists that were involved in this, they published a paper last week that appeared in the journal Science. I have Pascal Orich from the Yale University. He is the principal investigator on this. Also, Garth Illingworth comes back to us again from the University of California at Santa Cruz, and Richard Bones from Leiden University are all here to tell us about this thing. So Pascal, let me start with you. This is a confirmed observation. Now, we've heard before that there are other galaxies, maybe farther away. We've heard bigger numbers. I've even heard Z=10 galaxies. But this is a confirmed observation, correct? You want to describe to us what all that means?
Yeah, exactly. Yeah, well, thanks for having us on here.
You're welcome.
But yeah, so with Hubble, actually, we are able to push to even larger distances than for this particular galaxy here. But with Hubble, we can only get a rough sense of the actual distance of these sources. And so, we can use the Hubble images to give us some kind of indication of potentially how far away these galaxies are. But there's always some ambiguity. And what you really want to do here is get an actual distance measurement with a spectrum. I don't know, should we explain a spectrum is essentially?
Yeah, well, let's start. Before we do that, we should mention yardsticks of the universe, and we are talking about principally how do we know how far away things are in the universe. We use this thing called redshift. Now, many of our viewers already know what a redshift is, but we're going to very briefly. If you take a spectrum of an object in the sky, you'll see black lines that correspond to something called absorption lines, and where they are, and if they're shifted toward the red, and by how much, is an indicator of how far away things are. And that's the most accurate way of figuring out redshift. But there's another way, and the way that actually Hubble does best. It's something called photometric redshift. And Garth, I wonder if you might be able to give us an explanation of what that is. And at the same time, we have an animation that kind of describes this quite beautifully.
Certainly, Tony. Glad to do that.
Okay.
So with Hubble, it has separate cameras in the visible and working out into the near infrared, and each of those cameras has different filters, different colors that it can measure the light in. And
right,
so
Scott has an animation up. You can see all of the different filters and their band passes right there.
Right, exactly. And so what the cameras do is give us images in blue, in green, in red, and then out beyond where our eyes can see into the infrared. And as galaxies themselves, as we look at those more and more distant, they move to the red, as Tony was mentioning. There's classic redshift. And what the effect is there is that we see the galaxy in some filters, but not in others. And that is a very strong indicator that we're looking at a very distant galaxy. And how distant can be worked out from which filters it appears in. And so you can see there in the graphic, as it moves across, that it disappears in the blue, and then in the green, and then in the red, and ultimately it's way out into the infrared.
So that gray, what is that gray thing? Describe that gray thing that's moving.
Yeah,
what is
so that actually is a representation of the light from a galaxy spread out as a spectrum in its colors. And so you can see that gray thing that's moving across, it has a very sharp edge in the blue side. And that actually is how we really determine the redshift with Hubble. It's one of the fortuitous effects in the spectrum that arises from the hydrogen in galaxies and in the universe. And as you go further out, that hydrogen absorbs more of the light and absorbs the bluer light.
So Scott, at some point in the middle, can you stop that animation, or do you have that kind of control? Like right there. Okay, that's fine.
Sure.
So here we go. We've had this thing. This is the gray area is the light from the galaxy itself. And if it were not moving relative to us, we would see it across all band passes, correct?
If it was close.
If it was closed. But
that's right.
That whole thing is shifted. We can see how we can get a measurement of how far away it is. And notice in that filter, that purple filter, if you were to point the purple filter at this particular point where it says F435W, you wouldn't see anything. But you point the blue one in there, F606W, you'd see something, a little bit. And it would be even brighter in all these other filters. And from that, you can say, well, that's about a z equals 5 distance or something like that.
Yes, right. And that's about 1.3 billion years from the Big Bang.
And one of the things...
This galaxy, sorry, I'm just going much earlier than that. So
right.
More to the red.
And the thing, and I just want to touch on that thing that's falling away. As you get about halfway across, something disappears. What is that? What's
that's the effect of even more and more hydrogen in the universe as we're getting out to a point where there's more galaxies between us and the object we're looking at, and increasingly neutral hydrogen gas in the universe. And so that's eating away at the spectrum also, and making that break even sharper, which is great because it helps us more accurately estimate the redshift.
So, Pascal, this galaxy was at about z equals 8, which means that it's very bright in the red and maybe even a little bit of the yellow filters, but not so much at all in the blue filters, correct?
Yeah, exactly. Yeah.
So, again, I want to iterate. This is something called the photometric redshift, and it's got its problems, right? It's not super accurate. You can measure or infer a distance using these techniques, but it's not perfect, is it, Pascal?
Yeah, I mean, well, it gives you, because we were looking at the colors from the Hubble images, so it gives you a rough indication of how far away these sources are. but not exact, obviously, because the galaxies are different. They look different and so on. And also there's noise, of course, in our measurements. Plus, there's the biggest problem, I guess, is that potentially lower redshift galaxies or galaxies closer to us can, mimic some of these colors sometimes. In particular, as we go to the farthest distances, it gets more and more difficult to pick out the really, really distant sources from, something that is much closer but looks similarly red, for instance, as these high redshift galaxies. And so that's, that's the problem with this technique.
Right. So we've had many hangouts on before where we've talked about most distant thises and that's, and almost all of them were based on Hubble observations exclusively, which uses this photo Z component. But there's this observation that you're announcing and that you published last week in Science. This one is different because it's confirmed. You've got a really good idea of this distance. Can you explain that a little bit further?
Yeah, so just to clarify, it was published in Astrophysical Journals.
Oh, I apologize. My apologies.
Okay, yes.
I thought it was Science.
It was an exciting result anyway, but
yeah.
Yes. Yeah. So what we're doing then so the problem about these very distant sources is that they are also very faint. And so it's difficult to then actually confirm these sources with our spectrographs. So the distance measurement comes from a spectrum, as we were sort of saying before, and by essentially looking for emission lines for sort of what hydrogen emission lines that what we're using. By looking at where these lines actually are and comparing to where we think they should be from in the local universe, that's where we measure the redshift. And so once you have an exact line, you know exactly how far away this galaxy actually is. And so that's what we did with the Keck Mossfire spectrograph.
Okay, so I have a picture here of the Keck Observatory. I just want to show it really quick. Here's a picture of Keck on the mountain of Mauna Kea in Hawaii. Here it is shooting down alien spacecraft, but no, these are actually lasers for guide stars. But it is a really great telescope. It's got a lot of instruments on it, and one of the things I like the most is this right here. It's got a primary mirror that looks extremely familiar to me.
JW.
It looks a lot like this thing right here, which is going to go out in 2018. So this is the James Webb Space Telescope, and this is one way to make a very large mirror out of a bunch of smaller ones. And the Keck instrument was the one used to follow up these observations, but it used the spectrograph, right? Or it used an actual spectrum. Which is, as you say, vital to getting this down. What did Spitzer do? What was Spitzer's role?
So with Spitzer, with Hubble, we can sort of see the rest frame, the blue light. We can only measure sort of very young stars. We can only see very young stars. And with Spitzer, we have a different, even further to the red. We're probing a different wavelength range, so different type of light. And in particular, it allows us to actually measure masses of these galaxies. So we're
I'm sorry. Scott has a real nice graphic showing the wavelength coverage for Spitzer versus Hubble. So yeah. Go ahead.
Yeah, that's right. So if you look at this image here, so on the left you see the Hubble images, and again, as we were showing before, in the three left images, essentially it disappears because it is so distant. And then we see it in these two F125 and F160. So these are two different filters of two different images in different wavelength ranges. And then we also detect it here with Spitzer at two different wavelength ranges with two different filters. And obviously the Spitzer resolution is not as great as the one with Hubble. But it's really quite remarkable that we can, with this very small telescope, Spitzer, we can actually detect some of these most distant galaxies. And so that these two filters, they allow us to actually measure the mass of this galaxy. So we get the total stellar mass, all this, summing up all the stars and weighing this galaxy. And so that's how we found that it essentially only has about 1/6 or 1/7 of the mass of our Milky Way today.
Yeah, I want to talk a little bit about the actual properties of these early galaxies here in just a minute. But Richard, let me get you into this just a little bit. Can you tell us a little bit about some of what your role was in the team and what some of your interests were in this research?
Well, I was one of the people who did the initial field work, where I was surveying many large areas of sky, trying to essentially collect large numbers of these distant objects that to put into catalogs.
Were you using Keck for that, or what were you using?
For using the Hubble Space Telescope. So taking these big, large surveys where we've looked over basically a very large area, which in the end is pretty close to the area of the Moon. Something
wow, that's a lot of pointings. We all know the Hubble does not have a wide field of view, so that's a lot of pointings.
So you have to look at a lot of different pointings, and so I was looking out and systematically putting a lot of these different galaxies that we were seeing into a catalog, and in that catalog we were we were sorting the objects and trying to find those objects that were very bright and also very, very distant. And so my role was in essentially putting together this big list of objects, and it's like, oh, this one right here looks like a very, very distant, very bright object. And so I was the one who provided some of these lists to effectively Pascal, and we effectively looked at some of these lists together, and we decided that, for example, these objects that Pascal looked at with Keck, that they would be very good objects to effectively look at and to take spectra of, because we might find something very interesting.
Okay, so give us a sense for how that works. So you systematically looked at an area of sky about, like you say, the full moon, which is a lot of pointings of the Hubble Space Telescope. You must have had a lot of orbits, right?
Those were it's a public program. It was part of the big Candles program.
Oh, it was part of Candles. Oh, okay.
Candles program had 900 orbits of time, which is let's see, if we think about what 900 orbits is, 900 orbits
it's bunches,
would roughly correspond to a month and a half, or I'm not sure, a few months.
Yeah, Candles, for those of you who don't know, I forget the acronym, and I'm sure that you can tell us, but there's several surveys that have been going on using Hubble at the Institute. One of them was CLASH, another one was Candles, and we have Frontier Fields going on now. Candles was a big survey that that looked at that. So this is part of that work then.
Yeah. So basically, it was a part of that big work where they effectively looked over a very large area of the sky, 5 different parts of the sky, and the total area of roughly the size of the Moon, and again, spending something as something like a month and a half to 2 months of telescope time, just surveying this area of the sky. And so I was systematically looking through this area, through this whole area, trying to use the different filters, the flux in the different filters, plus using information from other telescopes looking at the same area of the sky to decide which objects look like some of the best candidates for super distant galaxies. And so then after we had that list, then Pascal and I looked at that list, and then we also looked at the fluxes of those objects with Spitzer. And when we looked at the fluxes of the object with Spitzer, I don't know if maybe I should let one of the other people talk about this, but because it's effectively moving to a new topic. But with Spitzer, Spitzer can give you information also on the redshift, because it turns out that some of these objects have very, very strong emission lines that occur at specific wavelengths, and they occur at wavelengths that the Spitzer Space Telescope is sensitive to. And so if you can if you can use Spitzer to figure out where the strong emission line is, it can give us another measurement, or approximate photometric measurement of the redshift, or approximate distance to the object, telling us, we should look at, for example, this very bright source here and not that bright source there.
Okay, so Scott, we had a nice fly through there that you had put together, or that you had sort of shortened for us. If you could put that up while we could take a look, because I want to take a look at this thing. So Richard and even Pascal, maybe you can comment. This was all, I like to emphasize these surveys and how we find these galaxies. They're not really done by a person sitting there looking at these things. They're done by software primarily. And here we got the fly through. So this is the field, and we see a bunch of distant galaxies and some other objects, and there's different shapes and sizes of all the galaxies. But the one that we're talking about here is going to come up in just a minute. It's going to be in red right at the center. Not a very remarkable looking thing, even though its adorable name would betray that.
This is not actually the one galaxy we targeted, but it's a source in the Hubble Ultra Deep Field. What we're seeing here is a fly through the Hubble Ultra Deep Field.
Okay, so this is a representative galaxy.
But it's at the same distance, roughly,
okay.
roughly
So
the
it's
same
something
distance.
not very remarkable. Garth, tell me a little bit about the earliest galaxies in the universe. What are they like?
Yeah, one thing I just wanted to add to the previous discussion was that one of the powers of Hubble and of Spitzer is that these huge data sets are publicly available from the very beginning and open to everybody to use.
That's true. That's true.
So
Same is true
this
for
has
frontier fields.
enabled international collaborations to work on these data sets and do great things with them. So, yeah, so we're now, as the video I think just showed, and it went back in time through the extreme deep field, which is part of overlapping the Hubble Ultra Deep Field. And you see as galaxies, you go deeper into that image, you see the galaxies becoming smaller and redder. And so we're pushing back in time there to very early times. In fact, that object that appears at the end is a very similar redshift, but a photometric one that we've seen with the field in candles at around the redshift 8, so around 650, 670 million years. But it doesn't have the certainty of the measurement that we have. And so that is what Keck has given us, as Pascal emphasized, a very definitive result for where this object is in time, where it is in the universe, or how far back we're looking to it.
Right, that's an important point about this press release and this paper you've written, is that this is a confirmed distance. This really is a z=8 galaxy, and we know it from the various observations. So I'm glad that we're emphasizing that part of it. What else do we know about this galaxy? It's just a fraction of the size of our Milky Way, right? Is that
yes, it is. That's right. So one of the fascinating things when we look at these galaxies in the image, they look red. But in fact, if we teleported ourselves back there, they would be small, they would be a vivid blue color, because they're forming stars 80 times faster, even though they're only a sixth of the mass of our galaxy. They're forming stars 80 times faster, they have big bright blue stars in them. It would sort of be like boiling cauldrons of stars, vivid blue stars forming in those early times.
I want to just very quickly interrupt what you're saying, because it's directly relevant to this YouTube comment. This is from Julian Gita, I think, from YouTube, said the galaxy was red and yellow up close, or is it UV and blue, and we just perceive it like that due to redshift? That's the point you're making, right? If we were right there,
she's got it exactly right. And so yes, it's a very blue object. It's just that as we look at it, because of the effects of the redshift and the filters we use, it actually looks sort of red or yellow to us when we're actually measuring it. But when we actually try to portray these, we often will do it in a blue color, because that's what they would really look like.
Yep, good comment, and really hit right on the point. So, so the reason now these star. What else can we take? Well, Pascal, what else can we learn from this galaxy? What else have you been able to ascertain from these observations about it?
Well, so as Richard sort of was alluding to, that we actually found relatively peculiar, quite peculiar colors in this galaxy from the Spitzer images, and so that tells us that there is this very strong emission line. So this galaxy has been forming stars very, very rapidly, and also most likely it had gas that was very, very low in heavy element abundances, compared to galaxies today. And so we have these extreme emission lines in these early sources, and so that's because we have this exact distance measurement now, we can really make these kind of measurements, and starting to sort of build up a history of the heavy element production in the universe as well.
This is right. These are among the first stars that begin the heavy elements. As most people probably know, all of the things that make us up, anything after hydrogen, helium, and lithium, all of the elements in the universe up to iron, I guess, are provided to us via the stars. So that includes everything that makes us up and everything that makes up planets and our soda pop, everything. So
anything after iron has to be because of violent deaths of those stars.
Yes, that's right. So supernovae and the deaths of stars create everything else. So, okay, so the star formation, you've already said a little bit, is going on very rapidly here. Do we get a sense of how it compares with galaxies of today?
Yeah, so that's sorry. That's what Garth was pointing out. Okay. It's essentially 80 times faster than. Well, we have an estimate of this, and it's roughly 80 times faster than our Milky Way today, for instance, our galaxy. But one thing to point out is that this, particular galaxy is one of the brightest sources at these distances. It's not a typical galaxy at these distances. And one of the problems, of course, with getting a spectrum of a galaxy is that essentially you're dispersing the light, right? You're not looking like with Hubble. You're looking at a bunch of light in a given filter, but with the spectrum, you actually disperse the light. So it gets harder and harder to actually measure these, to have enough photons of these galaxies. And so that's why we sort of, we're constantly looking for bright sources that have enough photons for us to actually follow them up from the ground. So that's
what Richard was alluding to. He was saying they're looking for both bright and distant objects. These are things that are like sort of antithetical to each other,
Yeah.
Well, Adam Synergy has a related question, which is, as always, very good. He says that Hubble's Wide Field Camera 3 can do near-infrared slitless spectroscopy. Why is Keck Mossfire more suitable or capable in this case? Is it because of the photons, the brightness of the object? Why can't you use the spectroscopic abilities on Hubble?
Yeah, so I guess we're trying, and other people have actually big surveys to follow up some of these sources. And for instance, in the frontier fields, there's a big survey going on, exactly using the weve GRISM spectrograph. The thing is that the resolution, unfortunately, of the GRISM is not as high as it is from the ground. And so with the GRISM, I'm not quite sure if this is absolutely true, but with the GRISM, I think you're better off, we're definitely better off getting a continuum spectrum than from the ground, versus for emission lines, maybe from the ground is somewhat easier, just because of the spectral resolution of the GRISM. But definitely we and other people are using the GRISM and are looking for these lines also.
Okay, good. So that good question, Adam, as always. Okay, go ahead.
Yeah, certainly, Tony. So, I think the GRISM is great. If people remember back to that object, that spectrum that we showed with the filters, that very sharp edge, that shows up very nicely in the GRISM. But the lines themselves tend to be these very peaky, narrow features, and they don't show up as well as on the GRISM from Hubble as they do with the Mossfire instrument. So they have complementary roles that they can play in searching for these objects and measuring the redshift.
Does Keck is Keck a limiting, or instruments or observatories like that, a limiting factor in this kind of research? I mean, we all know that Hubble is in space and that it can see things without the benefit of having to deal with the atmosphere. Do you have to be careful which objects you send over to Keck for verification, or is there any kind of limit?
Yeah, I would say, I mean, there definitely is. Partly it's because on the ground, the atmosphere absorbs some of the light in the infrared, and there are also very strong features that come from the night sky as well, which make it very hard often to detect an object, a spectrum, a line in the spectrum. So it's more challenging.
You mean things from maybe our own galaxy, or what do you mean?
No, this is from the atmosphere itself.
Oh,
so
I see.
The oxygen lines and so on in the atmosphere, there are structure in the night sky which can mimic and overlap what we're trying to measure. That makes it hard. And
Right.
The sky is brighter. Space is a wonderful place to put a telescope, which is why we're working all out to get JWST up there. Even though it's smaller than the Keck telescopes, it's going to be amazingly powerful.
Right.
And it also says why we're working to do 30 and 40 meter telescopes on the ground. That's partly then so that we can get more light and offset the effects of the atmosphere.
And one thing I like to point out about ground-based observatories that a lot of people don't realize is why they're located where they are. Places like Mauna Kea and the Chilean Andes and those kinds of places are ideal for ground-based telescopes because of one thing, and that is you want very dry conditions in the atmosphere, places where you don't have a lot of water vapor, because it turns out that in the infrared, where all the interesting stuff is going on, water vapor can absorb all of that. So that's why you see them built in these kinds of places, high in the mountains, but very little rainfall, very arid conditions, because the drier the atmosphere, and believe it or not, even though it is Hawaii, on top of 14,000 feet, it's pretty dry up there. I've been there, and it's cold, too. You ever go from the beach at Hilo all the way up to Mauna Kea? It's quite a difference. You need to bring your partner.
It's true. I was just talking with some people over at Carnegie about GMT, about the Giant Magellan Telescope, and once you're getting to those altitudes, when it comes to the seeing, when we're talking about that astrometric seeing,
yes,
they're actually looking at the off-gassing of the rocks. So they actually get geologists involved now too on actually covering up the base of where they're at to make sure that none of the gases that are coming from the ground itself are interfering with the atmosphere too. So it's getting to the point where even the seeing, we're getting a limit to how much that is, and we can offset by just the geology that is surrounding the area. So that's why different parts of the Atacama Desert are being chosen in Chile.
Okay, so I have a question from S. Dodger on the Q&A app, which is kind of related to what you were talking about other sources, but it's a little different. He's asking, what is the difference between these distant galaxies and the cosmic microwave background? I think he means in terms of age of the universe, how far back we're going, that kind of thing. Anybody want to take that?
Yeah. So the cosmic background was emitted from a time where there were no galaxies yet, right? That was just a recombination of the electrons and protons to produce hydrogen, essentially, and so that happened about 380,000 years after the Big Bang.
Very soon after.
Well, yeah, compared to our galaxy, which is 670 million years after the Big Bang. Yeah, that's a long way back. That's 95% the age of the universe that we're probing back with this particular galaxy. But yeah, there was not a whole lot of time in any case for this source to actually build all its stars and build the mass that it has already.
Okay, so I've got a question for myself. We've been talking about distances, ages of the universe, things like that. In terms of the number Z, we said this is a Z equals 8 galaxy. What is that number? What does it mean? What does Z mean when you say that? Z equals 8.
C equals 8 is essentially it gives us a measure. So 1 plus C is essentially exactly the wavelength, or the factor by which this wavelength is shifted to a longer wavelength, essentially. So that's the redshift. 1 plus C, C is the redshift, gives us exactly this measurement of how fast a galaxy is moving away from us, and how far away it is from us.
And it's a dimensionless number. It doesn't have any units, correct?
Right. Yes.
Yeah, so it's just a number. And Scott has something up here. What does he put up? This peak here. Is that the?
That's our spectrum. Yes. So this is on the top. Essentially, you see the. So this is the data that we actually got from the Keck Mossfire spectrograph. It's not, it's difficult to see, but on top you definitely.
Oh no, it's beautiful. It's absolutely beautiful. Yeah, it's going to be my new desktop background right there.
Oh my God! All right, So on top you see the two-dimensional spectrum, and so this darker dot in the middle, that's this emission line that we were measuring, and on the bottom you essentially see just a summed-up flux from this galaxy, and you see it at a wavelength of 1.06 something micron, and intrinsically this line came from Lyman alpha, which is an emission line, an infrared emission line, and at about 1,200 angstroms, and so we know so by comparing this wavelength where we're actually seeing this line and where we know it's coming from, we get the redshift, and that's redshift C 7.73.
Nice, and you seem to know it pretty well. That's a pretty good. That's a pretty small error bar there, plus or minus. So
yeah, once you find the line, yes, you know the redshift pretty well.
Which is why this is such an important follow-up observation. So
exactly.
Okay, so really good. Well, good. Thank you. I wanted to clarify that. Let me, Scott.
Can I just take us back to that question about the microwave background? If there's
of course.
That is a fascinating question, because as Pascal said, the microwave background really tells us about what the universe was like at 380,000 years and before. But our galaxy, which was very young, was at 670 million years, and there's a fascinating tale of what happened between then. Between when the hydrogen and the helium became common throughout the universe, permeated the universe at 380,000 years, there was a dark ages. 100, 200 million years, there was nothing going on in the universe except the dark matter was coalescing a little and building up. And so during that time, gas was starting to come together and collapsing, and then that led to the first stars, probably about 100 to 200 million years after the Big Bang. So a period which we call the Dark Ages was then followed by this dramatic burst of life, as it were, of starlight in the universe. And so we're seeing that then a few hundred million years after those very first stars and galaxies. But we're pushing back with Hubble not as far as we would like into that first part, because Hubble is limited. And that's
right.
what
pretty much reached its
really
limit.
will do. Take us back into the first stars and galaxies themselves.
Exactly, and that's what's so great about frontier fields is they're kind of cheating a little bit by using galaxy gravitational lensing to boost Hubble's power just a little bit more to see a little bit further back. But those
I wouldn't call that cheating. I would call that awesome. I mean, we're able to find natural lenses out in the universe by something that we don't completely understand, and being able to do that, I don't see how it's cheating. We're learning more about dark matter.
Clever usage of nature. How about that? Is that better?
There you go.
Sounds good.
Okay. Clever use of nature, not cheating. I guess I can see your point. Okay, Kieran, on a related issue, Kieran T is asking from YouTube, what is the highest redshift observed, and does it correspond to the age of the universe? I think what we're talking about tonight is the highest redshift observed.
Yes, I think as Pascal was saying earlier, that we have the highest confirmed redshift, which is 7.7, 670 million years after the Big Bang. We have looked, and we have photometric measurements from frontier fields and also from other fields.
Why did you...
Oops, Garth is muted.
Oops. Can you unmute yourself? You somehow got muted, Garth.
It'll be on the top of your screen there. It might look red.
Sorry, I don't know how that happened.
Yeah. No, I didn't know either.
Yeah,
and so where was I? Did I mention something?
You were being too amazing, and the internet couldn't handle it. We had to tone you down a little bit.
Yes. So as I was saying, the period with this particular object we've measured very accurately. That's 670 million years. But Hubble has let us push back a little, but with considerable uncertainty, back to about 450 million years at redshift 10 to 11.
Right,
So
we've had hangouts where we mentioned that with Dan Coe
that's
et al.
Pretty much the limit of what Hubble can do. Beyond that, it cannot do because it doesn't go far enough into the infrared. So again, this is why we're waiting for JWST.
I couldn't agree more. It's going to be ideally suited to look at this exact area. Another one from Galaxia, and I think this is related. I was being a little misleading before with the fly-through. Does this galaxy lie outside the Hubble Ultra Deep Field? If so, in what sense do we have a new HTF at all, and in what direction is this galaxy located? This was part of the CANDLE survey, and the fly-through was the Hubble Deep Field or Extreme Deep Field, and I may have misled you. But where is this galaxy at, Pascal?
Yeah, so essentially it's in this field called Aegis, so that's why the name EGS, and that's in the constellation of Bootes. And so it's not in the Hubble Deep Field at all. It was from the CANDLE survey, and again, as we were saying, we were looking for some of these brightest sources, and if you want to study extremely bright sources, unfortunately, you have to go to extremely large areas. And so, the Hubble Ultra Deep Field, where there's this pencil beam, and we're getting a huge amount of information, of course, on these very distant galaxies, but they are just extremely, extremely faint. And they're essentially, most of these galaxies in the Hubble Ultra Deep Field that we're seeing are much too faint that we can get a spectrum of and actually measure an exact distance before the James Webb, of course.
Oh, that's a good point. I didn't realize that. So really, the ones in the ultra deep field aren't going to get these confirmations like the ones you've been finding, right?
There may be a few, but the
most
very brightest ones. But most of them are too faint. Yes.
Oh, that's interesting. I didn't know that. Okay, thanks, Galaxia. And finally, Robert Karma is making a comment. I remember when critics said Hubble was a bust and that NASA was incompetent. Look at how much great science has been made over the past 25 years. This is the best time machine we have ever built. I couldn't have said it better.
Except the TARDIS. I don't know. The TARDIS and Hubble are neck and neck as far as I'm concerned. But we get a little bit more science on Hubble.
Scott, that was a TV show.
No, it's real.
Hubble really
No, the doctor's real.
No, it really does things, yeah.
He took me to Gallifrey once, I promise.
All right, Scott, look around Twitter. Is there anything I'm missing?
Nothing but just a lot of people really engaging and retweeting and sharing out the images I've been sharing and sharing out our YouTube link. Let's see, Mick Beaker was really liking the animation that we did of the extreme deep field to help as more of an analogy of how far back we're going.
Yeah, so we can thank Frank Summers for that and Greg Bacon et al. For those animations.
He said that the first deep field changed his life, and he loves that image. So we're looking at objects that are that far back, and that I think it does. It gives humanity an amazing perspective on things that are extremely difficult to even fathom. And now when we're able to put a precise date on it, that really helps us get a better understanding of what was going on at that time in the universe and how the evolution of the universe has come to be.
Awesome. Yep. Garth, I think this one's for you. I have one for Charles Bell. Hi, Charles. It's good to see you again. It's always nice to see your questions. How far in redshift do you expect with JWST?
Very interesting question, because one of the key questions that it relates to is just how bright these early galaxies are. I think that we have a good chance of pushing back to redshift 15, maybe 20, depending on whether we can find some nice bright galaxies there, and that is getting back to very early times.
I know. I've heard Jason Calderai and Massimo Stiavelli, they both say we're going to be looking at the first stars, people, the very first stars, and that is, it just doesn't get any.
Yeah, exactly. This is first stars and galaxies. That's what it's about.
Yeah, exactly.
Well, it'll be for solar systems as well, but we'll take the first stars and galaxies for us.
I know, and then there's the whole exoplanet thing. It's going to directly image exoplanets. So there's a lot of good, exciting work. Most of it due to two big things. Three things: the fact that it's out in space in the L2 point, the fact that it's got such a large primary mirror, and the fact that it's got such a it's in the infrared. You get such infrared detectors.
That's right. So that's where we need to be able to see redshift 15 and 20.
That's right. I've always said the future of astronomy is in the infrared because it lets us see the past. So.
Yeah. Can I just say one thing about?
You sure can.
One of the really amazing things, the most revolutionary things probably about the James Webb is that it is going to have a spectrograph on board that actually can measure these particular galaxies that we're seeing now in just amazing detail. And as we were saying before, with Spitzer, we see these very peculiar colors, and they give us a hint of this galaxy being, rapidly forming stars and having a strange, low element abundance in its heavy element abundance in its gas. But with James Webb, we can actually take a spectrum of this, and it's just going to be amazing. And so we're going to get a huge increase in our knowledge on physics of these sort of galaxies.
And that's near spec, right? Where you're talking about near spec?
Yes. Yeah. Yes. And and it's really important now to use sort of the next few years with Hubble before James Webb is launched to get more of these sources and get more targets for James Webb in its early years.
Well, Oh, go ahead, Garth. I'm sorry.
Yeah, I was just going to say, and also the other instruments there are grisms as well. So exactly as Pascal said, it's going to be a spectroscopic capability. And what that is going to be really important for, Pascal emphasized this is one of the brightest galaxies at this time. So it means it's a very rare and unusual object. And we're not looking at the typical galaxy. And if we want to understand how galaxies grew, we need to look at a typical object. And so James Webb will let us do that with the spectrographs.
Can you you've said the word several times and we didn't define it. What's a grism? Just real quick, can somebody define that for us?
Oh, it's a prism. People can think of just a prism spreading out the light. They may have had one at school or wherever and held it up to the sun and seen the light spread out. It's basically that, with some rulings on it, but it basically is a prism.
With
so it's not a prism held by a grizzly bear?
Oh, Scott, I'm so glad you're here to clarify things. Yes.
Exactly.
It's a very tried and true scientific method is to go in the lab, grab a grizzly bear, and give him a prism. And,
well, you put some rulings on
I'm
it
in California. Well. We have the bears out here, so.
So it's a combination of a grating and a prism. Let's put it that way.
There we go.
Yeah.
Okay. So, all right. As we move on, so so Pascal, I just want to ask you. I alluded to this at the top of the hangout, but I wanted to. This, I have a feeling, is not the end of it, right? I mean, we're going to be seeing more distant galaxies from Hubble, correct? Are you working on anything else?
Oh yeah, we definitely hope to, break the record, soon.
Break your own record, huh?
Yeah,
exactly.
yeah.
If we don't do it, somebody else will.
Exactly. Yes. No, I mean, this is a very active field of research. Obviously, I mean, as I said, having an accurate distance measurement really helps enormously in pinpointing the physical properties of these galaxies, etc. And so that's something several groups are trying to do. And unfortunately, now at the moment we only have a handful of galaxies with accurately measured distances more than 13.0 billion light years in the past. So it's really it's tough. It's very difficult. We're pushing our telescopes to their limit. But we're finding more and more of these sources with Hubble as more data come in, and as we're refining our search techniques, etc. And we're definitely hoping to push this further.
Good. Well, I hope that you do break your own record, and if you do, you'll come back and talk to us about it. If not, we're going to talk to those guys, whoever beats your record. So keep looking, Richard. I know you're out there looking at the data right now. So get the ones. It sounds to me like the trickiest part of this whole thing is not just finding these distant galaxies that Hubble has estimated using photo Z, but also finding one that can be followed up by ground-based observatory. That sounds to be the real tricky thing to me. So good luck, guys. Thank you for being on our hangout. I want to thank Pascal, Garth, and Richard for all taking the time out to tell us about their exciting discovery. The paper the paper was published in AppJ last week. So I got it right that time. And you can also check out more on HubbleSite.org in our news center.
The full paper's up there. So
that's right. We have a link to the paper up there as well if you want to delve in even more. Well, Scott, we got another one in our belt. Next week, we are going to be talking about white dwarfs and star and globular clusters in 47 Tuc. And next week, Carol should be back. She is out on assignment.
Out on assignment.
I've always wanted to say that. Sounds so BBC.
She's undercover in Tucson.
Not really. Not really. She's in Tucson Airport and doesn't have very good connection. Anyway, Carol will be back next week, and we'll pick up with because it's all about globular clusters, one of her favorite topics. So we hope you'll join us. I want to, on behalf of Scott and all of our guests, I want to thank you all for watching. Thank you for your comments and questions. Follow us on @Hubble Telescope. Also subscribe Hubble Site channel on YouTube. We'll see you guys next week. And as always, keep looking up. Hola.
Did Tony freeze?
There?
I believe Tony froze. So hi, everybody. Welcome to this week's Hubble Hangout. After a few weeks on hiatus, we are back after the 25th anniversary. And we are going over some amazing, amazing observations that have been made not only with the Hubble Space Telescope, but also with Spitzer and confirmed by Keck. And I think Tony's feed's coming back. I'm not sure. Are you there, Tony?
Am I there now? Am I there?
You are there.
Okay.
So I'll let you take it from here.
All right, thanks, guys. Well, we are, as Scott said, we are back from our very short hiatus, and we are getting ready. We have a very interesting hangout planned for you today. My name is Tony Darnell. I work at the Space Telescope Science Institute, and today's hangout is all about, and get ready to hear these words a lot, folks, astronomers using the Hubble Space Telescope have found a new most distant galaxy. And the reason you're going to keep hearing this in the future is that astronomers are pushing Hubble pretty hard to look at some of the earliest galaxies in the universe. And so this is all in advance of the James Webb Space Telescope. We're trying to learn as much as we can about the very early galaxies that were first formed. And in this case, the galaxy is very adorably named EGS-S to tell us about this thing. So Pascal, let me start with you. This is a confirmed observation. Now, we've heard before that there are other galaxies, maybe farther away. We've heard bigger numbers. I've even heard Z equals 10 galaxies. But this is a confirmed observation, correct? You want to describe to us what all that means?
Yeah, exactly. Yeah, well, thanks for having us on here.
You're welcome.
But yeah, so with Hubble, actually, we are able to push to even larger distances than for this particular galaxy here. But with Hubble, we can only get a rough sense of the actual distance of these sources, and so we can use the Hubble images to give us some kind of indication of potentially how far away these galaxies are. But there's always some ambiguity, and what you really want to do here is get an actual distance measurement with a spectrum. I don't know, should we explain a spectrum is essentially?
Yeah, well, let's start. Before we do that, we should mention yardsticks of the universe, and we are talking about principally how do we know how far away things are in the universe. We use this thing called redshift. Now, many of our viewers already know what a redshift is, but we're going to very briefly. If you take a spectrum of an object in the sky, you'll see black lines that correspond to something called absorption lines, and where they are, and if they're shifted toward the red, and by how much, is an indicator of how far away things are. And that's the most accurate way of figuring out redshift. But there's another way, and the way that actually Hubble does best, it's something called photometric redshift. And Garth, I wonder if you might be able to give us an explanation of what that is. And at the same time, we have an animation that kind of describes this quite beautifully.
Certainly, Tony. Glad to do that.
Okay.
So with Hubble, it has separate cameras in the visible and working out into the near infrared, and each of those cameras has different filters, different colors that it can measure the light in. And
right,
so
Scott has an animation up. You can see all of the different filters and their band passes right there.
Right, exactly. And so what the cameras do is give us images in blue, in green, in red, and then out beyond where our eyes can see into the infrared. And as galaxies themselves, as we look at those more and more distant, they move to the red, as Tony was mentioning. There's classic redshift. And what the effect is there is that we see the galaxy in some filters, but not in others. And that is a very strong indicator that we're looking at a very distant galaxy. And how distant can be worked out from which filters it appears in. And so you can see there in the graphic, as it moves across, that it disappears in the blue, and then in the green, and then in the red, and ultimately it's way out into the infrared.
Anniversary of the Hubble Space Telescope.
That's right. So if you haven't followed us on @HubbleTelescope on Twitter, you need to do that, and also subscribe to our YouTube channel, Hubble Site Channel, and you'll be able to catch all the announcements as they come out. So looking forward to hearing from you, and if any of your comments or questions come through as the comment or as the hangout progresses, I'll read them out there. Otherwise, I'll wait until the end. So as I said before, a new most distant galaxy ringing in at about 15% of the mass of our sun, EGS ZS8-1, was seen by the Hubble Space Telescope at a time when the universe was about 670 million years old, which means that the first photons left that galaxy and then traveled over 13 billion years before its feeble photons landed on the detectors of our venerable Hubble Space Telescope. But that's not the only instrument that used it. We also have observations from Spitzer and observations from the ground-based observatory on top of Mauna Kea, known as Keck. So we'll be talking about how all of these instruments work together. And the scientists that were involved in this, they published a paper last week that appeared in the journal Science. I have Pascal Orich from the Yale University. He is the principal investigator on this. Also, Garth Illingworth comes back to us again from the University of California at Santa Cruz, and Richard Bones from Leiden University are all here, ZS8-1, and we are going to talk all about its properties and characteristics and things like that. But before we get going, I want to remind you guys that while the Hubble 25th anniversary is officially over, the actual date of the anniversary, there's still going to be events going on all year long. So I would invite you to visit Hubble 25th is very important, .org, and go and check out whatever events are going on in your area and around the country for Hubble 25th celebrations. So we hope you can do that. We also want to, and before I introduce my guest for today, I want to remind you that we are very much interested in hearing from you. So we hope that you will give us your comments and questions. We've got a lot of interesting things to talk about today. And Scott Lewis, the driver of the internet, can you please tell these kind people how they can interact with us?
Absolutely. So the best and easiest way for us to answer your questions and comments is to use the Q&A app here on YouTube and Google+. You can utilize it both there. So on the bottom left-hand side on YouTube, you'll see that we are answering questions, and you'll be able to input those questions there. We will see them and select them, and we'll timestamp it and let us actually place those in there when they're answering your questions. We're also live tweeting this, so we're using the hashtag Hubble Hangout. So I'm sure you see it down here on the very bottom. And also we'll be checking out Hubble 25 as well, because it is still a celebration of the 25th